Let us see what we will cover today. Week 6, Insurance Claim Severity Prediction, Regression. Welcome to Data Mining in Python. This week we will work with a real-world insurance claims dataset. You will learn what regression is and why we use it, how to clean and explore insurance data, how to build, train, and evaluate a regression model. Can your model predict claim costs well? Let us find out. Running the cell now. Let us talk about regression. What is regression? Regression helps us predict a number, not a category. For example, predicting insurance claim amounts using features like age or smoking status. Running the cell now. First, let us turn off warnings so our notebook looks clean. We add code to stop Python from displaying warning messages. Import numpy as np. We set the random seed to 42 for reproducibility. Running the cell now. Here, we've set a random seed and suppressed warnings to ensure our regression results are consistent and clean for this lesson. While there's no visible output, this setup is crucial for making our predictions reproducible and focused on understanding the regression fundamentals ahead. Let us load the insurance claims dataset and preview it. This marks the start of our insurance dataset project. We use pandas to read the data from its online source. We define the web address of the data file. We load the CSV file into a data frame for easy data work. This prints out the shape to show us how many rows and columns there are. We display the first 3 rows to get a quick sense of the data. Running the cell now. This output shows the insurance dataset with 1,338 rows and 7 columns, including features like age, sex, BMI, and smoker status, along with the target variable for charges that we want to predict. Notice how the columns contain both numerical and categorical data, setting the stage for regression to estimate the numeric insurance charges based on these inputs. This initial look helps us understand the data structure before building our regression model. Try changing the URL to another open CSV online and see what happens. Now we will see what each column means in our dataset. Dataset columns. The insurance dataset includes age of the person, sex, male or female, BMI, body mass index, children, number of children covered, smoker, whether the person smokes, region, area of the US, charges, medical claim amount, what we want to predict. Running the cell now. Let us summarize the dataset and check for missing values. We display a summary of columns, types, and counts using the info method. This prints the number of missing values per column to help us spot data gaps. Running the cell now. This output shows the dataset has 1,338 rows and 7 columns, all fully populated with no missing values, which means our analysis can proceed without handling null data. Notice the mix of data types, integers for age and children, floats for BMI and charges, and objects for categorical fields like sex and smoker. This overview confirms our dataset's readiness and helps us plan appropriate data processing steps in the lesson. If you see missing values, think of ways you could fill them. Let us get quick statistics on our dataset. This prints a statistical summary of the data frame, showing measures like count, mean, STD, minute, and max for each numeric column. This prints summary statistics like mean and minute for numeric columns. It helps us spot outliers and get a feel for the values. Running the cell now. This statistical summary gives us a quick overview of key columns like age, BMI, children, and charges. Notice the typical age is around 39 years, with BMI averaging about 30.7 and charges ranging widely up to over 63,000, highlighting variability in insurance costs. This helps us understand the data distribution and informs how we might model or analyze these features later. Can you spot anything surprising in the mean or max values? Now, we will plot how the claim amounts are distributed. We make a histogram to show how many people fall in each range of claim costs. We import matplotlib for plotting. We set the plot size for easier viewing. We plot a histogram of the target column, charges. This labels the x-axis with what it measures. This labels the y-axis as frequency, meaning the count per bin. We add a title to the plot to explain what it shows. This displays the histogram chart. Running the cell now. This histogram shows the distribution of insurance charges, highlighting that most claim amounts are clustered at lower values, with a long tail extending towards higher charges. Notice the right skewed shape, which indicates a few people have very high medical costs. This visualization helps us understand the variability in charges before exploring factors like age or BMI that might influence them. Many real-world costs are spread out like this. Try plotting another numerical column. Let us see how much more smokers pay for insurance on average. Here we group the data by whether the person is a smoker. We then find the average insurance charges for each group. Running the cell now. This output shows the average insurance charges grouped by smoker status, revealing that smokers incur significantly higher average charges than non-smokers. Notice the clear difference in these mean values, which highlights the strong impact of smoking on healthcare costs. This connects to the lesson by demonstrating how grouping by key categorical columns, like smoker, can uncover important trends in the data. What feature do you think would matter a lot for insurance pricing? Let us check the link between age and the claim amount. We make a scatter plot to see if older people tend to have higher claim charges. We set up the chart size. We plot each person's age against their claim amount. Points are faded for easier reading. We label the x-axis with age. We label the y-axis with charges. We give our plot a clear title. This displays the scatter plot. Running the cell now. This scatter plot shows the relationship between age and insurance claim amounts, charges. Notice the wide spread of charges across all ages, with some higher charges clustering around middle-aged individuals, indicating potential age-related trends in claim costs. This visualization helps us explore how age might influence insurance charges before deeper analyses. Practice: try using a BMI instead of age for the x-axis. To use the data in models, we have to turn text into numbers. Regression models need numbers, not words. We use one-hot encoding to turn columns like sex, smoker, and region into numerical values. This prints the first 3 rows of the encoded table. Running the cell now. This output shows the first 3 rows after one-hot encoding the categorical columns sex, smoker, and region. Notice how each category is converted into a separate binary column, with values indicating presence, true, or absence, false, which prepares the data for modeling. This step is essential to handle categorical data in machine learning algorithms that require numerical input. When you try a new dataset, check if you need to encode its categories. Next, let us set up our model inputs and outputs. We split the table into features, everything except charges. We select the features by dropping the charges column from the data frame. We set the claim cost column as our prediction target. Running the cell now. Here, the code splits the dataset into features, x, and the target variable, y. Notice that x contains all columns except charges, which is isolated in y, reflecting the intent to use features to predict insurance charges. This separation is a key step before training a machine learning model. Always double-check your feature and target split before modeling. To check how well our model works, we split the data into training and testing sets. We import a helper that splits data for us. We use 80% of the data to train and 20% to test. Setting random_state equals 42 gives us the same split every time for fairness. We print how many rows are in our training set. We print the size of the test set for comparison. Running the cell now. The code splits the dataset into training and test sets, with 20% reserved for testing, as reflected in the output counts of 1070 training and 268 test samples. This ensures the model can learn from the majority of the data while preserving a separate set for unbiased evaluation, a key step in building reliable predictive models. Try adjusting test_size and see how it impacts your results. Now we scale our features so they have similar ranges. We import a tool called Scaler to make features even. The scaler shifts and stretches the numbers so all features are on the same scale. We fit the scaler only on training data to learn how to scale. We apply the scaler to transform the training features. We use that same scaling to transform the test features. Running the cell now. This code standardizes the features in the training and test sets, transforming them to have a mean of 0 and a standard deviation of 1. Although there's no direct output shown, this step ensures that columns like age, sex, and BMI are on the same scale, which improves the performance and convergence of many machine learning models. Notice that we fit the scaler only on the training data to prevent data leakage. Scaling helps many models learn faster and better. Let us build and train a basic linear regression model. We import a simple model for predicting numbers. We create the model instance. We train the model using our scaled training data and the claim amounts. The model learns how each feature relates to insurance costs. Running the cell now. This output confirms that the linear regression model was successfully created and trained using the scaled training data. Notice that the simple linear regression object indicates the default settings were used, aligning with our goal to establish a baseline model for predicting insurance charges based on features like age, sex, and BMI. This step is essential before evaluating model performance in later sections. Now we use the trained model to predict new claim amounts. Make predictions on the test data using the trained model. Store the predicted values for the test inputs in y_pred. Display the first 5 predicted insurance charges. Running the cell now. The output shows the first 5 predicted insurance charges from the model, with values ranging from around 7,000 to over 36,000. Notice how these predictions vary widely, reflecting differences in features like age, sex, and BMI used by the model. This demonstrates how the model translates the input data into specific charge estimates, linking back to understanding the dataset columns. How close are these predictions to the real values? Let us see how well our model predicts claim severity. This comment explains that we are evaluating the model's performance. We import functions to calculate how accurate our model's predictions are. This calculates the average absolute difference between predicted and actual values. This calculates the average squared difference, emphasizing larger errors more. This calculates how well the model's predictions explain the actual data variation. This prints the mean absolute error with 2 decimal places. This prints the mean squared error with 2 decimal places. This prints the R² score rounded to 3 decimal places. Running the cell now. This output summarizes the model's accuracy in predicting insurance costs, showing a mean absolute error of about 4,181, meaning on average the predictions are off by this amount. The R² score of 0.78 indicates that roughly 78% of the variance in costs is explained by the model, which is a strong fit. This evaluation confirms that the features like age, sex, and BMI are effectively capturing key factors affecting insurance charges. Practice, try using only a few features to see if your scores get better or worse. Visualizing predictions helps us quickly spot patterns and problems. We set up a scatter plot of actual claim amounts versus what our model guessed. We size the chart for clearer viewing. Each point shows one prediction and its real value. This adds a red line showing where perfect predictions would land. We set the X label as actual charges. We set the Y label as predicted charges. We give a clear title summarizing what is plotted. The plot is displayed. Running the cell now. This scatter plot compares actual insurance charges to those predicted by the model, with points clustering near the diagonal red line indicating accurate predictions. Notice how most points lie close to this line, demonstrating the model's effectiveness in estimating charges across the range of values. This visualization helps us evaluate prediction quality and spot any systematic errors in the model. Can you tell from the plot if the model is biased or accurate? Want to try your own prediction? Enter your info below. Prompt the user to try entering their own data for a prediction. Ask the user to enter their age as an integer. Ask the user to enter their BMI as a floating point number. Ask the user how many children they have as an integer. Ask the user to specify their sex, either male or female. Ask whether the user is a smoker with yes or no. Ask the user to specify their region from the 4 given options. Create a dictionary with the entered age, BMI, children, and placeholders for one-hot encoded categorical variables. Set the sex_male feature to 1 if the user said male, otherwise 0. Set the smoker_yes feature to 1 if the user said yes, otherwise 0. Set the region_northwest feature to 1 if the user picked northwest, otherwise 0. Set the region_southeast feature to 1 if the user picked southeast, otherwise 0. Set the region_southwest feature to 1 if the user picked southwest, otherwise 0. Convert the dictionary of features into a pandas data frame which the model can accept. Use the previously fitted scaler to transform the input features to the correct scale. Run the scaled input through the model to get the predicted insurance claim cost. Print the predicted insurance claim severity formatted as a dollar amount. Running the cell now. This output shows a predicted insurance claim cost based on the user's input for age, BMI, children, sex, smoking status, and region. Notice how the code converts categorical inputs into binary columns and scales the features before making the prediction, demonstrating how raw user data is prepared to match the model's training format. This highlights the importance of proper data pre-processing in obtaining accurate insurance cost estimates. Ask a friend to enter their info and see how the model responds. Make sure to like and subscribe if you enjoyed this hands-on demo. Let us try a random forest, which learns with multiple small decision trees. Random forest models are more flexible than simple regression. We import and build a random forest with 100 trees for more robust learning. We fit the forest to the same training data. We make predictions on the test set. We print out the R² value to compare with our earlier model. This lets us see if more complex models can capture patterns missed by linear regression. Running the cell now. The output shows the random forest model achieving an R² score of about 0.87, indicating it explains 87% of the variance in insurance charges on the test data. This high score suggests the model captures key patterns between features like age, sex, and BMI and the target variable. It demonstrates the effectiveness of tree-based regressors in modeling complex relationships within the insurance dataset. Practice. Try changing n_estimators and see how results change. Let us summarize what we learned today. Recap what we did. This week, you explored an insurance claims dataset, cleaned and visualized features, built linear and tree-based regression models, evaluated model accuracy. Next time, try more datasets or add extra features to improve your predictions. Running the cell now. A big thank you for following along. Thanks for learning with us. Keep experimenting, try adding new features, or tune your models. See you in the next lesson, and subscribe for more hands-on data science. Running the cell now.